So, good day. Let's learn how to graph complex numbers. All right. Yesterday we learned about the arithmetic of complex numbers, and so now today we would like to graph complex numbers. So, how do we do this? A complex number is written in the form a plus bi. It's a two-part number. The a and the b are both real numbers. So what we do is we make that a and b an ordered pair like this. Now this ordered pair represents not only an ordered pair in a graph, but it represents a complex number, okay? And so because of that, we can use this ordered pair to graph on our normal graphing system, rectangular graphing system, except there's one big difference. When we draw the axes, this is now called the real axis, and this is called the imaginary axis. So this will be the number for the real part of a complex number, which is the a, and the imaginary part of the complex number, the b, will be graphed in the y direction. So we label the axis differently. So if you have the complex number 2 plus 3i, then that can be rewritten as 2, 3, and we can therefore graph it like this. All right? Now, that's it. That's how you graph a complex number. Do negative 2 plus 4i. Well, that would be negative 2, 4 as an ordered pair. That would be right there. Okay? So, it's not like learning new graphing. It's just applying graphing to a new kind of number. Okay? Now, let's go to the next part of this. So if you remember when you first learned about absolute value of a number is how far a number is from 0. So if we look at a number line and we take like the number 3, then the absolute value of 3 is really the distance to 0 on a number line. All right? And so the absolute value of 3 is therefore equal to 3. This is the geometric definition of absolute value. Now, in the same way, you could take negative 4 and you want to know the absolute value of negative 4. Again, how far is that from 0? Well, it's a distance of 4. All right? So we're trying to get back to 0. That's what absolute value was. Well, what about a complex number? What if we had 2 minus 3i? All right? And we want to find the absolute value of that. So if you look at 2 minus 3i and you just graph it in the complex plane, we want to find out how far is it from 0. So in other words, we want to find how far is it from the origin. All right? So we're really asking how far is this point from the origin? Well, if you look at that, that is basically the distance between this point and the origin. Well, if I call that distance, then I can use the distance formula to find the absolute value of 2 minus 3i. So the way this works, but an important part of that is when I do the distance formula, you'll see I'm just subtracting 0 in each case. Which means it's really just the squares, the square root of the sum of the squares of the coordinates of the complex number, which in this case is 4 plus 9, or square root of 13. So we would say that the absolute value of 2 minus 3i, all right. So as I was saying, we would say that the absolute value of 2 minus 3i is the square root of 13, or we would say the modulus of 2 minus 3i is the square root of 13. And that's how we would find the absolute value of a complex number, any complex number. All right? And so there's the whole thing, the whole explanation again. All right? Now, there's one more geometric aspect of this that we want to look at. So let's do that. So once you get to the complex plane, you start to think, oh gosh, well, how do I add numbers geometric? How do I add complex numbers? Can I do it visually? Now, if you go just like we did the absolute value, if you look at the number line, all right, on a number line, suppose we want to find 2 plus 3, then we would go to 2, and then we would add 3, all right, add 3, which would be 3, 4, 5, and that would tell us 2 plus 3 is equal to 5. And so when we first learned about adding regular numbers, we did it geometrically on a number line. So in the same way, we can do this on a complex plane. Of course, it's a little different. So let's take 2 minus 3i, and we want to add to that 1 plus 4i. All right? So 2 and minus 3i, there's this complex number. And then we want 1 and 4i, which is right there. And so if we do this, there's our two complex numbers. So what we'd like to do is we would like to find the sum of these two complex numbers. And so what you do is you do the same slope and the same distance, all right? And I'm doing that from each point. So in other words, what we're doing is we're adding these pointwise. So we go 2 minus 3i, and then we add 1 plus 4i, all right? Just stacking up the complex numbers end to end. In the same way, you could have done 1 plus 4i and then 2 minus 3i. In any case, you'd end up at this point. Once you get to that point is your solution. And if we look at that, that looks to be about at 3 and 1i. So this looks to be at 3, 1, or 3 plus 1i. All right? And there's this complex number sum. It's essentially the diagonal of a parallelogram. All right? And in fact, if we add these together, we get 2 plus 1 plus negative 3 plus 4i, which is equal to 3 plus 1i. And that looks to be pretty close to what we have right here on my paper when we added them geometrically. And so if you do this on graph paper, you can do it actually very nicely. Now, what are a couple of things to pay attention to when adding geometrically? Well, if you have a complex number, say we have a complex number, all right here, then whatever, and you have another complex number right here, then if you go to this complex number and you want to add this one to it, you need essentially the same rise over run, the same slope. All right. So you're going to tack it on right there, and then this should have the same slope as that one, the same rise over run. So you're going to create a parallelogram. Opposite sides are parallel. All right? And once you do that, then the sum turns out to be the diagonal that meets at that opposite corner. All right? And whatever the ordered pair is for that opposite corner, that is your new complex number, or the sum. Now, if you do subtraction, basically you add the opposite of the vector. So if I did 2 minus 3i and I subtracted 1 plus 4i, then essentially I'm going to have my 2 minus 3i, that vector, and then I'm going to add the opposite of this vector, which is negative 1 minus 4i. So I graph the negative 1 minus 4i, that's the opposite, and I'm going to add these two vectors together now. And so again, I would do same slopes, and that would give our new solution. All right, which looks to be about 1, negative 7. Okay, and so 1, negative 7 should be right about there. All right, okay, now there's one kind of weird problem, not a weird problem, it's an important problem that they do in your lesson, and I want to talk about it. Oh my gosh, you just watched me do all this work. You just see all this work here, but I muted myself the whole time. So let me see if I can talk you through it quickly. What's happening, what your book lesson does is they want to try and show you how to prove the triangle inequality. They also talk about how in geometry class, in order to prove that, you had to draw an auxiliary line and do some stuff like that. And in fact, we were only proving it for real number lengths of triangles. So it turns out, if we change these to complex numbers, and we're trying, so we take a complex number here, and we add the two complex numbers, all right, to get this complex number here. So this complex number A, this complex number B, and we're going to add them to get complex number C. So we still get the triangle inequality. Looks just like the real number one I had above. However, complex number A could be some x plus yi Complex number B could be some G plus HI. And complex number C is the sum of those. So in other words, X plus G plus Y plus HI. If we rewrite this triangle inequality in terms of the complex numbers, where A equals X plus YI, B equals G plus HI, and C equals the sum A plus B in complex numbers, then we get this right here, okay? Then we get that right there. And what I attempt to do from that point on is to do exactly what they do in your lesson. I have different variables here, X, Y, G, and H. But what I do is I assume this is true. I assume the quiet triangle inequality is true. And it should lead me to an identity, something that is always true. If it does, then that means I could do the work backwards, which means this is the triangle inequality is true. And so the way I do that is I square both sides first. When I square both sides, I get these two things, okay? I then multiply out this right side and cancel out the terms that would subtract out from both sides. I then, in this step here, notice that there's a factor of 2, which I divide out. I then square both sides again and get these two statements here. Once I get those two statements, I multiply the one on the left and the one on the right, I square it. And then I subtract out the like terms again. And that ends me up right here. Now, at this point, if I subtract the 2xgyh on both sides and I rearrange it, it turns out that that factors to xh minus yg quantity squared. But on the right side, I have 0. So if I can say that this is always bigger than 0, bigger than or equal to 0, that means it's a true identity. And I can say that because anytime you square something, anytime you square it, it's always positive. So this is always greater than or equal to 0. And therefore, everything I have done from before is true and can be repeated backwards. And therefore, we have proved the triangle inequality. And this is what your lesson does. And I wanted you to see it, that it's really only algebra. Now, I'm sorry I didn't record it while I was writing it, so you kind of see it all done, but it works. And if you can square both sides, collect like terms, etc., going through this, then you should get it. The only thing that should be new is the substitution of the complex numbers into this triangle inequality form. And then you got to square that or write the moduluses, which is what I do in this step. All right? In any case, it proves true. Now, what this leads to is sort of a strange little problem that they do where you use the triangle inequality to help you with that. And so they use it in this form. And so I want to show you that now. They write the triangle inequality as the modulus of complex number A plus the modulus of complex number B is greater than or equal to the modulus of the sum. And they do problems that I've actually never seen before. They have you do a problem where you find the range of these complex number values. So let me grab an example and I'll show you how it's done. So I snagged a problem, and what you need to do is really interesting. They give you something like this. The absolute value of A is equal to 2/5 x plus 2. The absolute value of B, so this is your first complex number. Your second complex number is like negative 3/4 x minus 1. And then the absolute value of the sum, or the modulus of the sum, A plus B, is equal to 2x plus 4. And then what they ask you is they ask you on what interval must x fall. Now, I've never seen this problem before. All right. And what we're doing here is we're assuming these are complex numbers. All right. And then their modulus is this variable situation. And what you need to do then is, because they ask you to do this problem, it'll probably show up on a quiz or a test. You need to be able to know how to do this problem, so I'm going to do it. Now, what I think is really important is what I've showed you before, which is how to prove the triangle inequality. But basically what we're going to do is we're going to do essentially the same thing to find the range of values for x. So between what numbers will x be? And so let's go ahead and start that, and I'll show you how to do it now. So where do you begin to figure out on what interval must x fall? All right. What's the issue here? Well, there are three things. What we need to know is that each of these moduluses individually, this one and this one, have to be greater than 0. So basically, you set these inequalities greater than or equal to 0. And you solve them. So 2/5 x is greater than or equal to negative 2. X is greater than or equal to negative 5 when you multiply both sides by 5/2. And then you get negative 3/4 x is greater than or equal to 1. Now we multiply both sides by a negative, so the inequality changes direction, and we get x is less than or equal to negative 4/3. Okay? And so we get these two inequalities. All right? So let's go to the next part of the problem. And then the third requirement is that the sum of the two is greater than the sum of the two individually is greater than the modulus of the sum. That's actually the triangle inequality. So we're going to add this one and this one, and it's going to be greater than or equal to that one. So the next inequality you write is 2/5 x plus 2 plus negative 3/4 x minus 1 is greater than or equal to 2x plus 4. And then you proceed to solve that inequality as well. So I'm going to do that. So there's a common denominator here of 20 on the left side, so I'm going to deal with it. Actually, the way I like to do these is I'm just going to multiply the whole inequality by 20. All right. So 8x plus 40 minus 15x minus 20 is greater than or equal to 40x plus 160. All right? And now I can do the x's. So 8x minus 15x is negative 7x plus 20 is greater than or equal to 40x. Excuse me, this should be 80, not 160, plus 80. All right, and then subtract the 40x, so negative 47x is greater than or equal to minus 20, 60. So x is less than or equal, because I divide by a negative 47, 60 47ths. All right? And so you have some requirements here. And what we want to do is look at them. So, and let me change color here and circle them. So here's one requirement. That's where the first modulus is bigger than 0. Here's another requirement where the second modulus is bigger than 0. And then finally, I forgot my negative sign here. Here's our third requirement right there. All right? And so what you have to do is you have to put all these inequalities together. Okay? And so basically, we're greater than, what I would do is I'd kind of look at this on a number line. They sort of, in the example problem, demonstrate this, not very visually. So what I have here is negative 5, all right? And I have x is greater than negative 5. And then I have x is less than or equal to negative 4/3. So negative 4/3 is to the right of negative 5. And so I'd have this inequality. And then finally, the last one is x is less than or equal to negative 60 47ths. Now, if you look at that, negative 60 47ths as a decimal, is equal to negative 1.27, which means it's slightly to the right here, negative 60 47ths, because negative 4/3 is negative 1.33, and this is negative 1.27. So it's slightly to the right, and we're less than that. And so the problem originally wanted us to find on what interval must x fall. So by meeting each of these conditions, the two individual moduluses are greater than 0, and then the third condition where the sum of the two individual moduluses is greater than the modulus of the sum, you get three inequalities, and basically you're looking on a number line for where they overlap. And where do they overlap? They all overlap between negative 5 and negative 4/3. All of them are in that range. So the solution is negative 5 is less than or equal to x is less than or equal to negative 4/3. All right? And that would be the solution to this problem. Any questions with that? You definitely want to bring that to class if you have any questions, okay? Do that on Thursday, all right? Okay, that's all I have for you with this video. Good luck. Let's review real quick. This becomes kind of a long video. And here's what this whole process on the last thing would look like. And so this is not the most important, but what are the most important things? The most important things are, can you find the modulus of a complex number? All right. Which again is its absolute value. All right. Can you graph a complex number? All right. Can you find the sum or the difference of a complex number on a graph? So if you're using nice graph paper, can you do that? All right. If you can do those three things, you know the essentials of what you need to know mathematically. And then the last thing would be the triangle inequality. The modulus of P plus the modulus of Q is greater than or equal to the modulus of P plus Q, where P and Q are complex numbers. And again, they have kind of a strange problem for you to do that uses this, but nothing totally unusual. So anyway, have a great day and enjoy yourself. All right. Bye.